So I want to set the stage for our lesson about reaction order by giving you an analogy about a hot dog eating contest. So let's think about how changes in the contestant situation could affect the rate at which hot dogs are eaten. This is our contestant, Bob. And we're going to say that we have an endless supply of hot dogs. And so we know that that's going to result in a certain number of hot dogs being eaten per minute. Let's say that Bob can eat about 6 hot dogs per minute. Okay? So now let's say that we change the contestant situation. So now it's Bob and just some other random contestant. Once again, an endless supply of hot dogs, but because we've doubled the number of contestants, then maybe that would result in doubling of the rate at which hot dogs are being eaten. Now 12 hot dogs are being eaten per minute. So now let's change the contestant situation again. So instead of just some other random contestant, now let's say that Bob is competing against his #1 rival. So that might bring out the competitiveness in each of them. And so now with an endless supply of hot dogs, that might result in 24 hot dogs being eaten per minute. So remember that the original rate was 6 hot dogs per minute. So now we've doubled the contestants, but we've quadrupled the rate at which hot dogs are being eaten because of the competitiveness of these two guys. So now, instead of the #1 rival, let's say that Bob is competing surprisingly against an old friend that he hasn't seen for a really long time. So as you can imagine, now maybe instead of spending all of his time shoveling hot dogs into his mouth, and the same thing for the friend, that they're spending some time catching up, talking to each other. And so as a consequence to that, maybe the rate at which hot dogs are eaten didn't change from the baseline. It still sits at 6 hot dogs eaten per minute. So we notice that the change in rate of hot dogs eaten depends on the type of the contestants. It depends on the nature of our contestants. Okay, so just in summary, Bob could eat 6 hot dogs per minute. So that's like our baseline. And we know that if Bob just has another competitor, then that caused a doubling of the rate at which hot dogs were eaten. So we doubled the number of contestants and we doubled the rate at which hot dogs are eaten. So that shows that it's directly proportional. So another situation would be if we double the number of contestants, that could cause an exponential increase in the rate at which hot dogs are eaten. So it went up by a factor of 4, okay, which is 2 squared. It's an exponential, the exponent of 2. Or we could have a scenario where doubling up the contestants has no effect at all on the rate at which hot dogs are eaten. There's no relationship because chemical reaction rates can be affected in a similar way. So instead of thinking about how changes will affect the rate at which hot dogs are eaten, we're going to think about how changes will affect the rate at which reactants transform into products. So instead of Bob, we're going to call them reactant A. And instead of an endless supply of hot dogs, we're going to call that reactant B. And instead of monitoring the rate at which hot dogs are eaten, we're going to monitor the rate of a reaction. And that's usually in units of molarity per second. One important thing to note is that in order for us to really isolate the variables, we have to hold the concentration of all of the reactants except one constant. So in this case, we're going to hold the concentration of B constant so that we can actually observe the effect of A, changes in A on the rate of the reaction. Okay? So it turns out that what we need to look at, or we need to figure out, is we need to figure out the exponent on the change factor so that we can classify what's called the order of the reaction for that reactant. So let's look at an example. So let's say that I double the concentration of A. So instead of having just A, I have 2 times the concentration of A. And then we see how that affects the rate of the reaction. Remember, B is being held constant. So any change in the rate of the reaction is due to this doubling of the concentration of A. And so let's say that that caused the rate of the reaction to go up by a factor of 4. What exponent would I put on this multiplier to make this multiplier? Well, we know that squaring 2 makes it a 4. So that exponent is what's important. It's an exponent on the change factor is used to classify the order of the reaction for that reactant. So what I would say is that this is second order. Since that exponent is a 2, I would say this is second order reaction. In our original situation, Bob was our contestant, but in the chemical reaction, we said that that would be like reactant A. And so we said that 6 hot dogs per minute is our baseline. And so we're just going to say that the rate of the reaction under the initial conditions is our baseline. And so then the second scenario was when we had Bob and some other just random contestant. So that would be like doubling up the concentration of A. And in that scenario, we double the rate. We call that directly proportional. And so now in terms of the reaction kinetics vocabulary, we would call that first order in A. So if doubling the concentration doubles the rate, it's directly proportional, and we call that first order. Okay, well, the other scenario that we had was Bob and his #1 rival. So that's still just doubling the concentration of our reactant A, but that caused a quadrupling of the rate. So the rate went up by a factor of 4. Okay, and remember that we want to think about what exponent do I put on that multiplier in the reactant to make the multiplier on the rate. And so since 2 squared equals 4, we could say then that in this case, that would be a second order reaction in A. All right. And then finally, if we had Bob and an old friend, remember that that's still 2 contestants. So that's still like doubling the concentration of the reactant. But in that scenario, there was no effect on the rate at all. Okay. So what do we call that? Well, what exponent would I put on 2 to make the rate stay the same? And remember that anytime you put an exponent of 0 on something, it turns it into a 1. So that's like a multiplier of 1. So that's why we would call that scenario 0 order with respect to A. Okay? So the reason why this is important is because those reaction orders are what is going to tell us about the mechanism of the reaction. It helps us figure out the mechanism of the reaction. And that's a topic for another video.